The Mysteries of Interstellar Dust, a calm journey through space's hidden web. Before we begin our exploration of interstellar dust, take a moment to settle yourself. Find a comfortable position. Let your breathing slow and deepen. Release the tensions of the day. The universe is ancient and patient. It has existed for billions of years and will continue for billions more. Your worries, your cares, your daily struggles, all are temporary against the vast timescale of cosmic history. As we journey together through space and time, remember that you are made of stardust. The atoms that compose your body were forged in the cores of dying stars. You are connected to this universe not merely by observation, but by fundamental composition. We are all expressions of the same cosmic story. Segment 1. What interstellar dust is. Welcome to a journey through the cosmos, where we will explore one of the most fascinating and fundamental components of our universe. As you settle in, prepare to drift through the vastness of space and discover the secrets hidden in the darkness between the stars. This is a meditation on creation itself, told through the story of dust, those infinitesimal particles that shape the architecture of galaxies and make possible the emergence of life. Let yourself relax as we begin this journey. There is no rush, no urgency. Time moves differently in space. Millions of years pass like moments. Distances that would take a human lifetime to traverse are mere neighborhoods in the cosmic landscape. As you breathe deeply and let your mind settle, imagine yourself floating in space, surrounded by darkness and countless stars. Imagine vast stretches of space, seemingly empty and void. Yet this apparent emptiness holds profound mysteries. Between the stars, throughout the infinite expanses of our galaxy and beyond, floats something so small, so delicate, that it defies ordinary comprehension. This is interstellar dust. It is present everywhere in space, yet invisible to the human eye. It whispers through the cosmos in eternal silence, shaping everything we see and everything that exists. Interstellar dust consists of tiny solid particles floating in the space between stars. These are not the dust particles you might encounter on Earth, the bits of dead skin and household debris that accumulate on shelves and furniture. These are cosmic grains, fragments of material created in the cores of stars, scattered throughout the galaxy by the violence of stellar explosions and the gentle pressure of stellar winds. They have journeyed for billions of years through the darkness, survivors of cosmic radiation and collision, eternal wanderers in the void. Imagine particles so small that trillions of them would fit on the head of a needle. Yet each one is a complete world unto itself, composed of atoms arranged in intricate patterns, bearing the chemical signatures of the stars in which they were born. The size of these grains is remarkably diminutive. Typical grains are comparable in size to smoke particles or even smaller. Picture smoke curling through a sunbeam in a quiet room, and you begin to grasp the scale we are discussing. Yet even this comparison does not fully capture how minuscule these particles truly are. They are among the smallest objects that astronomy can directly study, existing at the boundary between the molecular and the visible. A single dust grain is larger than a molecule, yet smaller than a wavelength of visible light. This places dust in a unique position in the universe, able to interact with light in ways that neither molecules nor larger particles could manage. If you could somehow hold a dust grain in your hand, you would not be able to see it. It would be too small for your eyes to resolve, yet it would be composed of millions of atoms, organized in intricate structures that took billions of years to form. You might wonder how such tiny particles could matter in the grand scheme of the universe. Yet dust, despite its seeming insignificance, has outsized effects on nearly everything we observe in the cosmos. Dust makes up only about 1% of the interstellar medium by mass, yet this modest fraction shapes the structure and evolution of galaxies, influences the birth of stars, and even contributes to the creation of planets. The universe does not measure importance by percentage alone. A small amount of the right material in the right place can have profound effects. Dust is such material. 1% of the interstellar medium is a vast quantity when you consider the enormous volumes of space involved. All the dust in our galaxy, if gathered into a single heap, would form an object larger than the Earth. Yet this same dust, when spread throughout the galaxy, is nearly invisible, encountered only when it concentrates in particular regions. Most of the mass between stars is gas, vast oceans of hydrogen and helium that fill the darkness. Within this gaseous ocean, dust plays a distinct role. Dust is the solid, particulate part of the interstellar medium, the tangible substance that embodies properties entirely different from gas. While gas expands to fill available space, diffusing and flowing, dust remains as discrete, coherent particles, each one independent yet related to all others by gravity and radiation. Gas and dust interact constantly, influencing each other's behavior. Yet they remain fundamentally different in nature. Gas is the majority, dust is the minority, yet dust often dominates the behavior of the system. This is one of nature's paradoxes. The most abundant component often matters less than the rare one. Grains are large compared with atoms, but small compared with wavelengths of visible light. This places them in a unique position in the universe, able to interact with light in ways both profound and subtle. They are large enough to scatter and absorb electromagnetic radiation, yet small enough to remain suspended indefinitely in space, never settling or sinking, forever drifting in the cosmic void. A dust grain is large enough that it contains billions of atoms, yet small enough that radiation pressure from starlight can push it around. An atom is too small to interact effectively with visible light. A boulder is too large to remain suspended in space. A dust grain occupies the perfect intermediate position, large enough to matter, small enough to float eternally. These particles are often described as submicron particles, smaller than 1/1000th of a millimeter. To place this in perspective, if a grain of interstellar dust were enlarged to the size of a marble, 1 centimeter in diameter, then the marble would have to be enlarged to the size of the entire Earth, 10,000 kilometers across, just to maintain the same proportional relationship. We are discussing objects of truly staggering smallness. Yet these infinitesimal particles are not simple. They have structure, they have composition, they have properties that determine how they interact with light and with other particles. A dust grain, examined under the most powerful microscope, would reveal layers, surface features, impurities, and variations. Each grain is unique, bearing the marks of its particular history. Interstellar dust is sometimes called cosmic dust or IS dust in astronomy. These alternative names reflect the long history of astronomical research and the various contexts in which scientists discuss this material. Whether called dust, cosmic particles, grains, or particulates, all these terms refer to the same fundamental phenomenon, the solid constituents of interstellar space. The term cosmic dust emphasizes its universal nature, its presence throughout the cosmos. The term interstellar dust emphasizes its location in the space between stars. The abbreviation IS dust is used by technical researchers for brevity. All point to the same material, the focus of our meditation and exploration. Dust grains float freely in space rather than being bound to a solid surface. There is no ground beneath them, no ocean containing them, no atmosphere surrounding them. They drift alone or in loose aggregates, suspended in the near vacuum of space, subject only to the forces of gravity and radiation, the gentle pressure of light from distant stars, and the invisible influence of magnetic fields. This freedom gives them a strange kind of independence, allowing them to travel vast distances across the galaxy. A dust grain in the inner regions of the Milky Way might be carried outward by stellar winds and radiation pressure, taking thousands of years to travel thousands of light years. It might pass through dozens of different environments, each one leaving its mark on the grain's surface, altering its composition, changing its properties. By the time the grain has traveled around the galaxy once, returning to its starting point, it may be a dramatically different object from the grain it was at the beginning of the journey. These grains can travel vast distances, carried by galactic motions and stellar winds. When a star dies in a supernova explosion, it releases powerful winds that push dust outward for hundreds or thousands of light years. Even the gentle, steady winds from ordinary stars can carry dust particles on journeys of unimaginable length. And the rotation of galaxies themselves, the great wheels of stars and gas spinning through space, carries dust around orbits that take hundreds of millions of years to complete. A single dust grain might be carried dozens of times around a galactic orbit before being destroyed or incorporated into a star or planet. The journey of a dust grain through space is a journey through cosmic time, through epochs of stellar birth and death, through the evolution of galaxies and the unfolding of cosmic history. Dust is not evenly spread throughout space. It does not distribute itself uniformly, like some invisible fog suspended equally everywhere. Instead, dust clumps more densely in certain regions, particularly in molecular clouds, where conditions favor its accumulation and preservation. These regions become places of particular interest to astronomers, for where dust gathers, profound cosmic processes often follow. Here in these dusty clouds, stars are born and planets form. Here, in the darkness and density, chemistry unfolds that would be impossible in the transparent regions of space. The distribution of dust traces the gravitational potential wells that shape galaxies. Dust concentrates where gravity pulls most strongly, in spiral arms, in galactic nuclei, in the cores of molecular clouds. This concentration of dust is not random, but rather follows from fundamental physical principles. Dust, being particulate, responds to gravity like any other matter. Yet dust also responds to radiation pressure and magnetic forces in ways that gas alone does not. The result is a rich and complex distribution pattern that varies from region to region and changes over time. As we begin this journey, remember that dust, for all its invisibility and immeasurable tininess, is a key to understanding how our universe works. Every star you see in the night sky, every planet that orbits those stars, every breath you take owes its existence in some way to dust. Dust has shaped galactic structure. Dust enabled the formation of our solar system. Dust will shape the future of the galaxy and perhaps someday birth new worlds we cannot yet imagine. The humble dust grain, smallest and most numerous of cosmic objects, is also among the most important. In the coming hours, we will explore how this is so, traveling deeper and deeper into the mysteries of these cosmic particles. We will learn where dust comes from, how it interacts with light, what chemistry occurs on its surface, and how it shapes the destiny of galaxies. We will understand dust not as a mere background component, but as a central character in the cosmic drama. Segment 2: Composition and Structure of Dust. If we could somehow capture a grain of interstellar dust and examine it under the most powerful microscope, what would we discover? The answer to this question reveals a complexity hidden in microns and angstroms, a material science that rivals anything on Earth. The structure of dust is not simple, not monolithic. Rather, it is diverse, variable, complex in ways that continue to surprise and challenge astronomers and physicists. Interstellar grains are mainly made of silicates and carbonaceous materials. These two fundamental classes of dust compose the vast majority of all cosmic particles. Each serves distinct purposes in the universe. Each brings different properties to bear on the cosmic environment. Together, they form a complementary pair, two different materials that together create the diversity of interstellar dust. Silicates are minerals, rock-like materials based on silicon and oxygen. Carbonaceous materials are organic compounds based on carbon and hydrogen, ranging from simple molecules to complex polymers. In space, these two categories account for approximately 90% of all dust. The remaining 10% consists of ices, metals, and other exotic materials. Silicate grains contain elements like silicon, magnesium, oxygen, and iron. These are elements you know from Earth. Silicon forms the basis of sand and rock. Magnesium, iron, and oxygen combine to form minerals you can hold in your hand, like olivine and magnetite. Yet in the frozen darkness between stars, these same elements combine into structures vastly different from their earthly forms. The silicates of interstellar space are alien materials, shaped by processes utterly foreign to terrestrial geology. They are amorphous, lacking the crystalline order of terrestrial minerals. They form under conditions of near-perfect vacuum, in temperatures ranging from a few tens of Kelvin to hundreds of Kelvin, in radiation fields so intense they would destroy any material on Earth in moments. The silicate grains of space are, in some sense, more alien to Earth chemistry than any material we could synthesize in laboratories. Carbonaceous grains are dominated by carbon and hydrogen in various chemical structures. Carbon, the basis of all life on Earth, takes on different forms throughout the universe. In interstellar grains, carbon combines with hydrogen in intricate patterns, forming polymers and aromatic structures that endow these particles with distinct optical and chemical properties. Carbonaceous dust can be rich in aromatic compounds, benzene rings, and more complex ring structures, or aliphatic, with straight chain and branched carbon structures. The carbon in dust can also form fullerenes, buckyballs, exotic structures not found in nature on Earth until scientists created them in laboratories. The chemistry of carbon never ceases to surprise, even in the cold darkness of space. Many grains include both silicate and carbon components in different layers. Dust is not monolithic. Many grains, perhaps most grains, are composite structures with an inner core of one material and an outer coating of another. These layered structures form over time as the grain travels through different environments, accumulating materials, being processed by radiation, altered by chemistry. A grain that condensed in the cool stellar wind of an AGB star might be composed entirely of carbon-rich material. As it travels through space and enters a region of intense ultraviolet radiation, its surface carbonizes, becoming enriched in aromatic compounds. Eventually, it enters a cold molecular cloud. Here, water ice and other frozen materials condense on its surface, adding a mantle of ice kilometers deep on a grain-size scale. A single grain can tell a story of cosmic wandering and transformation, a biography written in atoms and molecules. Hydrogenated amorphous carbon is a common type of carbonaceous dust. Amorphous carbon refers to carbon that lacks crystalline structure, carbon arranged in irregular patterns rather than in the orderly lattices of diamond or graphite. When hydrogen atoms bond to this amorphous carbon, forming CH bonds throughout the structure, the result is hydrogenated amorphous carbon, often abbreviated HAC. This material is common in interstellar space. Hydrogenated amorphous carbon absorbs and emits light in distinctive ways, making it a key component in understanding what we observe when we study interstellar dust. The properties of HAC suggest that it is produced by ultraviolet processing of more complex organic materials, breaking bonds and driving hydrogen out of aromatic ring structures into more aliphatic forms. Amorphous materials lack long-range crystal order, giving grains a glassy nature. In a crystal, atoms arrange themselves in regular repeating patterns that extend throughout the entire structure. Every atom occupies a position defined by the crystalline lattice. In amorphous materials, atoms cluster more randomly without the geometric perfection of crystalline solids. This gives amorphous dust a glassy, almost translucent quality. If you could magnify such a grain and observe it closely, it would appear smooth yet disordered, like a tiny bead of dark glass frozen in space. The amorphous structure affects how the grain interacts with light and how it evolves under radiation processing. Amorphous materials can more easily transition into crystalline forms when heated. They can more easily be processed by ultraviolet light, as there are no perfect crystal faces to resist the radiation. Only a small fraction of interstellar silicates are thought to be fully crystalline. This is actually surprising to astronomers. We would expect, given enough time, that structures would crystallize and become more ordered. Yet observations show that most silicates remain stubbornly amorphous, suggesting that the processes that create silicate dust, or the subsequent processing it undergoes, actively prevents crystallization. The universe prefers disorder to order, or perhaps crystallization requires conditions that rarely occur in the interstellar medium. Silicate dust in young stellar systems and around AGB stars appears more crystalline. Silicate dust in older, more processed environments appears more amorphous. This variation provides evidence for how dust evolves over time and how different processes shape grain structure. Some grains have icy mantles made of frozen simple molecules. As dust travels through the densest and coldest regions of space, particularly within molecular clouds where temperatures can plunge to tens of degrees above absolute zero, simple molecules freeze out of the gas phase and coat the dust surfaces. These frozen layers, called mantles or ices, transform the dust grain from a bare mineral particle into something far more complex. An icy mantle can be thousands of molecular layers deep, a distance that is immense on the scale of nanometers, but completely invisible in bulk. The accumulation of ices transforms the optical properties of the grain, making it darker and more opaque. Ices may contain water, carbon monoxide, carbon dioxide, methane, and ammonia. These simple, familiar molecules, the building blocks of all chemistry, freeze into solid layers on dust surfaces. Water ice, the same material as ice on Earth, exists in abundance throughout the cold regions of space. In molecular clouds, water ice can comprise 40% or more of a grain's mass. Carbon monoxide and carbon dioxide, molecules associated with fire and breath on Earth, become part of this frozen coating. Methane and ammonia, substances we know from planets and chemistry labs, accumulate in these icy mantles. Together, these frozen layers create a complex chemical scaffold upon which further reactions can occur. The ices are not passive materials, but active participants in the chemistry of space. Ultraviolet light and cosmic rays penetrate the icy mantles, driving chemical reactions that create new molecules. Dust grains can also hold trace amounts of metals like nickel and calcium. While silicates and carbon dominate the composition of dust, metals also play a role, though in smaller quantities. Nickel and calcium, along with iron and other metallic elements, can be incorporated into grains during their formation or accumulate on their surfaces over time. These metallic components influence how grains interact with magnetic fields and electromagnetic radiation, adding another layer of complexity to their behavior. The presence of metals in dust also affects how the dust interacts with cosmic rays and radiation, as metallic components can transfer energy more readily than pure silicate or carbon grains. A large fraction of interstellar carbon is locked up in solid dust grains. This is a profound statement about the structure of our universe. Carbon, the element that forms the basis of all known life, exists in interstellar space in several forms, as gas molecules like carbon monoxide and carbon dioxide, as components of cosmic dust, as atoms in the gas phase, and in other configurations. Yet a substantial portion of all the cosmic carbon that fills the galaxy is bound up in these microscopic solids. Estimates suggest that between 20 and 30% of all carbon in the interstellar medium resides in dust grains. This enormous amount of locked-up carbon has profound implications for galactic chemistry and the abundance of carbon available for star and planet formation. Nearly all available silicon, magnesium, and much of iron are believed to reside in dust. When astronomers measure the abundance of various elements in space, they find that certain elements seem to be depleted from the gas phase. Silicon and magnesium, in particular, are far less abundant in interstellar gas than the abundance predicted by cosmic nucleosynthesis, the theory that describes how elements are created in stars and supernovae. Where do these missing elements go? The answer is dust. Most of the silicon and magnesium in the galaxy has been incorporated into dust grains. The same is true for much of the iron, another important element. This depletion is not uniform throughout the galaxy. In dense clouds, the depletion is extreme, with 90% or more of the silicon locked into dust. In diffuse regions, the depletion is less severe. The depletion of elements from the gas phase is one way dust content is inferred. Astronomers cannot directly photograph most interstellar dust, for it is too small and too numerous to resolve as individual particles. Instead, they use indirect methods. By measuring the abundance of various elements in interstellar gas and comparing these abundances to theoretical predictions, they can calculate how much material has been depleted into dust. This clever technique transforms an invisible component into something quantifiable and measurable. If silicon is depleted by 50% in a region, we can infer that approximately half the silicon has been incorporated into dust, and we can estimate the dust mass accordingly. Polycyclic aromatic hydrocarbons, or PAHs, are thought to form part of the smallest dust grains. PAHs are fascinating molecules belonging to a class of compounds that display remarkable properties. They are carbon molecules arranged in multiple aromatic rings, planar structures of breathtaking geometric perfection. These molecules are related to soot and smoke on Earth, yet in space they play a more fundamental role, shaping the radiation environment and contributing uniquely to the behavior of dust. PAHs are not dust grains themselves, but rather molecules that may be embedded in dust or float freely as individual molecules. Some scientists consider the smallest PAHs to be the smallest dust particles, blurring the boundary between molecules and dust. PAHs are flat, ringed carbon molecules related to soot and smoke on Earth. If you have ever observed smoke curling from a fire, you have seen soot, which contains PAH-like molecules. In interstellar space, similar molecules form through chemical processes and exist as a key component of dust. Their flat, ring-based structure gives them distinctive optical properties. The aromatic rings can absorb ultraviolet light very effectively, elevating electrons to higher energy states. When these electrons return to lower energy states, they can emit light in the infrared, creating signatures that astronomers can detect and study. PAHs constitute perhaps 5% of interstellar carbon by mass, yet their effects on dust properties are disproportionately large. Some grains may contain sulfides, oxides, and metallic inclusions in small proportions. The universe is endlessly inventive in creating variety. While silicates and carbon dominate, other chemical compounds also find their way into dust grains. Compounds of sulfur with metals, creating sulfides, can be incorporated into grains. Oxides of silicon and iron can form as separate components. Even small chunks of metallic material can be embedded in larger grains. Each of these components contributes its own properties, creating a rich tapestry of material that varies from grain to grain and from region to region. The diversity of dust composition reflects the diversity of chemical processes occurring throughout the galaxy. Carbonaceous dust likely spans a continuum from aromatic rich to aliphatic-rich material. Aromatic refers to molecules containing rings of carbon atoms, particularly benzene rings, which are energetically stable and display distinctive chemical properties. Aliphatic refers to carbon chains and more complex branched structures without these aromatic rings. The dust in space appears not to fall into discrete categories, but rather to display a continuous range of properties between these extremes, suggesting that diverse chemical processing creates diverse materials. This continuum reflects the history of each grain, with ultraviolet processing tending to increase aromaticity, while other processes increase aliphatic character. The hydrogen-to-carbon ratio in carbonaceous grains varies with environment and processing. As dust travels through different regions of space and is subjected to different forms of radiation and chemical exposure, its composition changes. The ratio of hydrogen atoms to carbon atoms in carbonaceous grains can shift significantly, reflecting the history of the grain. A grain that has spent time in a harsh ultraviolet radiation field will be processed differently from one that has resided in a protected cold molecular cloud. Young dust in stellar winds tends to be hydrogen-rich with more hydrogenated amorphous carbon. Older dust in diffuse regions tends to be more hydrogen-poor, processed by ultraviolet light that breaks CH bonds. Interstellar dust in different galaxies shows broadly similar components but different proportions. The universe, in its vastness, displays remarkable consistency in its fundamental building blocks. Galaxies, separated by billions of light-years, containing different generations of stars, with different histories and different metallicities, nonetheless produce dust with recognizably similar compositions. Yet the proportions of silicates to carbonaceous material, the abundance of ices, the distribution of grain sizes, all vary in ways that reflect each galaxy's unique history. This suggests that the physics of dust formation is universal, the same throughout the cosmos. Yet the history of each galaxy leaves its own particular imprint on the dust. Dust composition depends on the star formation history and metallicity of its host galaxy. A galaxy that has actively formed stars for billions of years, enriching itself with metals, will have a different dust composition than a young galaxy with fewer stellar generations. A galaxy with a history of supernova explosions will produce different dust than one where stars have primarily shed material through gentle stellar winds. The dust population of a galaxy is a living record of that galaxy's history, a testament written in particles of silicon and carbon. By studying the dust in galaxies, astronomers can learn about galactic history and evolution. Segment 3. The origins of interstellar dust. The dust that fills the galaxy did not always exist. It had a beginning, a moment or era of creation when the first grains formed. Understanding where dust comes from requires us to contemplate the life cycles of stars, the violent deaths that create new material, and the slow processes by which chemistry transforms gases into solids. This is a story of transformation, of matter changing form and substance, of the eternal cycle of creation and destruction that characterizes the universe. Dust is partly produced in the cool outer layers of aging stars. As a star ages and grows older, its internal structure changes fundamentally. For a star like our Sun, this aging process takes billions of years. But for massive stars, it occurs much more rapidly, on timescales of millions of years. Eventually, any star, whether ancient or relatively young, reaches a stage where its outer layers cool and expand dramatically. In these cool regions, the conditions are right for solid material to condense from the stellar atmosphere. What was gas becomes solid. What floats freely in plasma becomes bound in grains. This transformation occurs when atoms and molecules can collide and stick together in the cool temperatures, when binding energies are low enough that thermal motion cannot tear newly formed bonds apart. Red giants can shed material that condenses into dust in their stellar winds. Red giant stars represent an advanced stage in stellar evolution. These stars have expanded to enormous proportions, sometimes growing large enough to engulf the inner planets of their systems. The surfaces of red giants are relatively cool compared to massive young stars, with temperatures ranging from 3000 to 4000 Kelvin, cool enough for molecules to exist. The gravity at the surface of a red giant is weakened by its vast size, allowing material to escape easily, flowing outward into space as a gentle wind. As this material leaves the star and cools further, moving farther from the star's heat and radiation, simple molecules and then solid grains condense from the gas. A red giant sheds material at rates that can exceed a billionth of a solar mass per year, creating shells of dust that extend far into space around the star. Asymptotic giant branch stars are major contributors of carbon and oxygen-rich grains. AGB stars, as they are known to astronomers, are a particular class of evolved star that proves especially effective dust factories. These stars pulse rhythmically, expanding and contracting in cycles that take years or decades. This pulsation drives powerful stellar winds, carrying material rich in carbon and oxygen far into the surrounding space. In these cool winds, carbon and oxygen combine to form molecules like carbon monoxide and carbon dioxide, which condense into solid dust particles. The material ejected from AGB stars is often enriched in carbon relative to oxygen, creating an environment favorable for carbon-rich dust formation. Many of the carbon-rich grains detected by astronomers are believed to originate from these remarkable objects. AGB stars have been particularly important sources of dust throughout cosmic history, contributing significantly to the dust population of galaxies. Supernova explosions also eject dust into the interstellar medium, while stellar winds from aging stars create dust gently and gradually. Supernovae create dust violently and suddenly. When a massive star reaches the end of its life, its core collapses and rebounds in a cataclysmic explosion. This supernova event can, for a brief period, outshine an entire galaxy containing billions of stars. The explosion ejects material with such tremendous force that it creates temperatures and pressures appropriate for the formation of new dust. Material freshly created in the nuclear furnace of the stellar core is scattered into space as dusty material. Recent observations by infrared telescopes have detected substantial quantities of dust in supernova remnants, dust that must have been created in the explosion itself. Some of this dust is amorphous, some crystalline, reflecting the diverse conditions in the exploding star. Newly formed grains in supernova ejecta must survive intense shocks to persist. The dust born in the violent depths of a supernova explosion faces immediate peril. The expanding cloud of ejected material collides with the surrounding interstellar medium, creating shock waves of tremendous intensity. These shocks can vaporize dust, breaking grains apart, returning the atoms from which they formed back into the gas phase. For dust to survive in the aftermath of a supernova, it must be robust enough to withstand temperatures and pressures that would be catastrophic on Earth. A shock passing through a region of dust can heat the dust to temperatures exceeding 1000 Kelvin, hot enough to melt most materials. Some grains survive, their sturdy structures intact. Others are destroyed, their material recycled back into the cosmos. Circumstellar shells around evolved stars are considered factories of fresh dust. Around some aging stars, particularly AGB stars, lie shells of material ejected in previous pulsations. These shells, called circumstellar envelopes or circumstellar shells, surround the star like the layers of an onion. In these shells, conditions are ideal for the formation and growth of dust. The temperature is low enough for condensation, yet warm enough that chemical reactions proceed at useful rates. The density is high enough for collisions to occur frequently, yet low enough that the material remains gaseous. The shells are protected from intense external radiation fields, yet illuminated by the star's radiation. These shells are thus cosmic factories, continually producing new dust as stellar material is processed by chemistry and radiation. The shells expand outward over thousands of years, eventually dissipating into the interstellar medium, releasing their dust into the galaxy. Some grains may form directly within dense interstellar clouds via accretion and chemistry. While most interstellar dust forms in the vicinity of stars, some dust may also form within the depths of cold molecular clouds. In these dark, dense regions, simple atoms and molecules can encounter one another and undergo chemical reactions. Through repeated accretion of atoms and molecules onto existing seed particles, dust grains can grow. This process, occurring at temperatures near absolute zero and pressures that would be a nearly perfect vacuum by terrestrial standards, nonetheless allows dust to form and grow. The process is slow, taking millions of years for a grain to accumulate a significant amount of material, yet it contributes to the overall dust population of the galaxy. This in-cloud formation may be particularly important for creating the thicker, icy mantles observed on grains in dense clouds. Over time, dust populations represent a mixture of stardust and interstellar processed material. The dust we observe in galaxies today is not purely material freshly ejected from stars. Some of it is stardust, grains that condensed in stellar atmospheres and dusty shells and have maintained their identity through cosmic history. Yet much of it has been processed, altered by exposure to radiation and chemical reactions, modified by the environments through which it has traveled. Any grain of dust you might imagine contains atoms created in diverse ways and carried through diverse journeys. A single grain might contain silicon atoms created in a massive star billions of years ago, carbon atoms created in an AGB star 10 million years ago, hydrogen atoms that have existed since the Big Bang, and oxygen atoms created in a nearby star just a few million years ago. The grain thus represents a sample of cosmic history, a record in atoms. The dust life cycle includes formation, alteration, destruction, and regrowth. Dust is not static, not fixed in eternal unchanging form. Instead, it cycles continuously through various states. A grain forms, perhaps in a stellar wind or within a molecular cloud. As it travels through space, radiation alters its surface, changing its composition. In some environments, it may be destroyed, vaporized by heat or shattered by collision. Yet in other regions, material can accrete back onto surviving grains, rebuilding them. This endless cycle, this movement from formation to alteration to destruction and back to growth, continues throughout cosmic time. The cycle is driven by the environment. In harsh environments, destruction dominates. In gentle environments, growth dominates. The net effect determines whether dust abundance increases or decreases in any given region. Dust is constantly being recycled as stars form and die within the galaxy. The galaxy is not static. Stars are being born in molecular clouds, living their lives and dying, sometimes quietly and sometimes violently. Each of these events involves dust. Dust is compressed and incorporated into newly forming stars. If the dust is incorporated into a young star, it is eventually destroyed as the star's heat vaporizes it. Yet some of the atoms that compose the dust will be fused in the star's core, creating heavier elements. When the star dies, these new elements are returned to space, incorporated into new dust. Dust is shed by dying stars, enriching the interstellar medium with freshly created grains. Dust is destroyed in the harsh radiation fields near massive young stars. Dust is reformed in the gentle shells around aging stars. This constant recycling creates a dynamic dust population, forever changing, forever flowing, tied intimately to the great cycles of stellar birth and death. Over billions of years, the dust population evolves, becomes enriched in heavy elements and complex materials, changes in composition and abundance as the galaxy matures. Segment 4. Dust and the nature of light. Light is the voice of the universe. Through light, we perceive distant stars and galaxies, reading the messages written in photons that have traveled for years or billions of years to reach our eyes. Yet dust intervenes in this conversation, disrupting the message, changing the light that reaches us. Understanding how dust interacts with light is crucial to understanding both the nature of dust and the true properties of the objects beyond it. Light and dust engage in an eternal dance, neither able to exist without reference to the other. Dust grains scatter and absorb starlight, dimming stars viewed through them. When light from a distant star encounters a dust grain, one of several things can happen. Sometimes the light passes through unimpeded, continuing on its journey. But often, the grain intercepts the photon, either absorbing it or scattering it in a new direction. Absorbed light disappears, its energy converted to heat that slightly warms the dust grain. The energy of the photon is distributed among the atoms of the grain, increasing their vibrations, raising the grain's temperature. Scattered light continues on, but now travels in a direction different from its original path. It has been deflected, its trajectory bent by its encounter with the dust grain. In both cases, the observer looking toward that distant star sees a dimmer image than they would see if no dust were in the way. The star appears fainter, its light suppressed by the intervening dust. This dimming is called interstellar extinction and varies with wavelength. This is a crucial point. Not all light is equally affected by dust. The amount of dimming depends on the wavelength of the light. This wavelength dependence is one of the most important characteristics of dust, for it provides crucial information about the sizes and compositions of dust grains. If all wavelengths were equally affected, dust would simply reduce the intensity of light uniformly. But because shorter wavelengths are preferentially scattered and absorbed, while longer wavelengths pass through more readily, dust creates a distinctive pattern of extinction as a function of wavelength. This pattern is a fingerprint of dust, a signature that reveals dust's properties. Shorter wavelengths like blue light are more strongly affected than red light. Blue light has a shorter wavelength than red light. When light encounters an obstacle smaller than or comparable to its wavelength, the scattering is most effective at shorter wavelengths. This is precisely the case for interstellar dust. Most dust grains are smaller than the wavelength of visible light. A typical dust grain has a size around 1/10 of a micrometer, while the wavelength of blue light is about 400 nanometers or 0.4 micrometers. A dust grain is thus about 1/4 the size of a blue light wavelength and much smaller than the wavelength of red light, which is about 700 nanometers. As a result, they scatter blue light much more effectively than red light. This is not a unique phenomenon. You might have noticed that the sky is blue during the day and red at sunset. This same physics is at work. Shorter blue wavelengths scatter easily in the Earth's atmosphere, making the sky blue when the sun is high, while longer red wavelengths pass through more easily and dominate the light at sunset, when the sunlight has passed through more atmosphere. As a result, stars seen through dust appear redder than they actually are. If a star's light must pass through a cloud of dust to reach Earth, the dust removes blue light preferentially, scattering it away in various directions. The remaining light that reaches Earth is depleted in blue, enriched in red. The star, therefore, appears redder than its true color. This effect is purely due to the dust. The star itself has not changed. Yet an observer unaware of the dust would incorrectly conclude that the star is redder, perhaps cooler, than it actually is. This has profound implications for astronomy. Dust can disguise the properties of the objects beyond it, making them appear different from their true nature. This color change is known as interstellar reddening. Reddening is a distinctive effect produced by dust, and it provides astronomers with a powerful tool for detecting dust and measuring its abundance. By comparing the observed colors of stars with their true colors as determined from their spectra or their stellar types, astronomers can calculate how much reddening has occurred, and from this, infer how much dust must be present along the line of sight to that star. If a star's observed color indicates a temperature 3000 Kelvin hotter than its spectral type suggests, the astronomer knows that dust has reddened the light. By calculating the exact amount of reddening, the astronomer can determine how much dust lies along the line of sight. The pattern of extinction with wavelength is summarized in extinction curves. If astronomers measure how much light is dimmed at many different wavelengths, they can plot these measurements as a graph, with wavelength on one axis and extinction on the other. The resulting curve reveals the dust's composition and grain size. Different types of dust produce distinctive extinction curves. A dust population dominated by large grains produces a flatter extinction curve, with less dramatic changes from visible to ultraviolet light. A dust population with many small grains produces a steeper extinction curve, with extinction increasing more rapidly toward ultraviolet wavelengths. By examining extinction curves, astronomers can infer not only that dust is present, but also something about the sizes and types of grains that make up that dust. Extinction curves differ between diffuse regions and denser clouds. The interstellar medium is not uniform. In regions where the density is low and dust is sparse, called diffuse regions, the dust is typically bare or only lightly coated with material. In denser regions, particularly molecular clouds, dust grains have accumulated thick mantles of ice and other materials. These different types of dust produce different extinction curves. A dust grain with a thick ice mantle will scatter light differently than a bare mineral grain. The ice mantle covers the underlying silicate grain, changing how the grain's surface interacts with light. The extinction curve becomes noticeably different in regions with icy dust compared to regions with bare dust. A pronounced ultraviolet bump around 217.5 nanometers is a hallmark of galactic dust. In the ultraviolet portion of the spectrum, the extinction curve displays a distinctive feature, a bump or peak at a wavelength of approximately 217.5 nanometers. This feature is one of the most famous characteristics of the dust in our Milky Way galaxy. It appears consistently across our galaxy, making it essentially a fingerprint of galactic dust. Wherever this bump is observed, astronomers know they are dealing with dust from our own galaxy. In extragalactic dust from other galaxies, the bump may be present, but often has a somewhat different shape or strength, reflecting differences in dust composition. This ultraviolet bump is widely attributed to certain carbon-based grain components. The peak in ultraviolet extinction is thought to arise from polycyclic aromatic hydrocarbons, those PAH molecules we discussed earlier. These flat ringed carbon structures have optical properties that produce absorption and scattering in the ultraviolet, creating the bump in the extinction curve. This attribution connects what astronomers observe about extinction with the chemical composition of the dust, bridging observation and theory. Yet the exact physical mechanism by which PAHs produce this feature remains somewhat mysterious, an active area of research. Segment 5. The infrared signature of dust. When visible and ultraviolet light is blocked by dust, we must turn to other wavelengths to observe the universe. Infrared light penetrates dust far more effectively than visible light, allowing us to observe the hidden regions of space where stars are born and galaxies evolve. Dust, while obscuring visible light, emits its own infrared radiation, creating a window into the cosmos. Broad infrared absorption bands reveal silicate features at about 9.7 and 18 micrometers. When light interacts with dust in a different way, through absorption in the infrared rather than scattering in the visible and ultraviolet, distinctive features again appear. Infrared light can excite vibrations in molecules and crystal structures. Silicate dust, when illuminated by infrared light of the appropriate wavelength, absorbs light strongly at certain frequencies. These frequencies correspond to the vibrational modes of silicate minerals. Two prominent absorption bands appear at wavelengths of about 9.7 and 18 micrometers. These wavelengths, though they seem arbitrary, correspond to fundamental vibrational modes of silicon-oxygen bonds. Silicate absorption features are associated with SiO stretching and bending vibrations. Silicate minerals consist of silicon atoms bonded to oxygen atoms in various geometric arrangements. When infrared light strikes a silicate grain, it can cause these silicon-oxygen bonds to vibrate. The SiO bond can stretch and shrink, oscillating back and forth at a specific frequency determined by the strength of the bond and the masses of the atoms involved, or the bonds can bend, changing the angles between atoms. These vibrations occur at specific frequencies. When the infrared light's frequency matches the vibrational frequency of the bonds, absorption occurs. The light's energy is used to excite the vibration. Astronomers observing in the infrared can see these absorption features and identify silicate dust. The wavelength and strength of the features can even provide information about the specific type of silicate, whether it is olivine or pyroxene or another variety. Weak infrared bands around 3.4 micrometers suggest aliphatic carbon-hydrogen bonds in carbonaceous dust. Just as silicate dust produces distinctive infrared absorption bands, carbonaceous dust produces its own fingerprints. Infrared light can excite vibrations in carbon-hydrogen bonds within organic molecules. These vibrations produce weak absorption bands around a wavelength of 3.4 micrometers. The presence of these bands indicates the presence of aliphatic carbon, the type of carbon composed of straight chains and branched structures rather than aromatic rings. This provides astronomers with information about the specific type of carbon in the dust. If the 3.4 micrometer band is strong, we know the carbonaceous dust is rich in aliphatic material. If it is weak, the carbon is likely more aromatic. Additional infrared features trace more aromatic carbon-carbon and carbon-hydrogen modes. Aromatic carbon, with its characteristic ring structures, produces different infrared signatures than aliphatic carbon. The carbon-carbon and carbon-hydrogen bonds within aromatic rings vibrate at their own characteristic frequencies, producing absorption bands at different wavelengths than aliphatic carbon. Aromatic CH bonds produce absorption near 3.1 micrometers. Aromatic CC bonds produce features at longer wavelengths. By analyzing infrared spectra in detail, astronomers can determine not just that carbonaceous dust is present, but what specific type of carbon-based molecules comprise the dust. Complex computer models can fit the observed infrared spectrum with combinations of different dust components, revealing the likely composition. Dust also emits infrared radiation after absorbing starlight and heating up. When starlight strikes a dust grain and is absorbed, the grain's temperature increases. As the grain heats, its atoms vibrate more vigorously. Atoms and molecules can only vibrate at certain specific frequencies determined by the strengths of their bonds and their masses. When these atoms vibrate, they emit electromagnetic radiation. For moderately warm dust, this radiation falls in the infrared portion of the spectrum. Thus, dust becomes both dark in visible light and luminous in infrared. A dust cloud that appears opaque and black to our eyes glows with infrared light. When observed with infrared telescopes, dusty regions appear bright and luminous, revealing the hidden structures within. The infrared glow of dust thus makes visible what would otherwise be invisible. very small grains and polycyclic aromatic hydrocarbons can heat up and cool quickly, causing transient emission. Larger dust grains have substantial mass and take time to heat and cool. The thermal capacity of a large grain is large. Adding the energy of a single ultraviolet photon raises the grain's temperature only slightly. But very small grains, especially individual PAH molecules, have so little heat capacity that they can be heated by a single ultraviolet photon, rising to very high temperatures briefly, hundreds of Kelvin above the ambient temperature before cooling again. This causes them to emit intense but brief pulses of infrared radiation. The result is a type of emission that does not come from objects in thermal equilibrium, but rather from particles undergoing rapid temperature fluctuations. In a densely packed region of PAHS being bombarded by ultraviolet light, thousands of individual PAHS are emitting pulses at any given moment, creating a complex, fluctuating infrared glow. Dust emission shapes the infrared glow of galaxies observed by space telescopes. When astronomers observe distant galaxies with infrared telescopes, much of the light they detect is not the direct starlight from the stars within those galaxies. Instead, it is infrared radiation emitted by dust that has absorbed starlight. For galaxies rich in dust, the infrared emission can dominate, containing more energy than the visible light. This means that to understand a galaxy's true energy output and the true rate at which it is forming stars, astronomers must account for dust. The dust emission reveals the star formation happening within galaxies shrouded in dust clouds. Young galaxies in the early universe, forming stars at tremendous rates, are often completely invisible in optical light, but blazingly bright in infrared. In dense clouds, dust temperatures can be as low as only a few tens of Kelvin. In the cold, sheltered depths of molecular clouds, far from any sources of heat, dust cools to extraordinarily low temperatures. A few tens of Kelvin means just tens of degrees above absolute zero. At such temperatures, dust barely emits any thermal radiation. The dust is far too cold. At 4 Kelvin, dust emits radiation primarily in the submillimeter and millimeter portions of the spectrum, wavelengths so long that they are barely infrared at all. Yet this cold dust is crucial for observing star-forming regions. The cold dust outlines the densest cores within molecular clouds, regions where gravitational collapse is occurring and new stars are forming. By observing cold dust emission, astronomers can directly locate where new stars are being born. In harsher radiation fields, grains are warmer and radiate more strongly. Near young, hot stars, ultraviolet radiation is intense. Dust grains in these regions absorb more energy and reach higher temperatures. Warmer dust emits more infrared radiation and emits it at shorter wavelengths, shifting the emission toward the mid-infrared portion of the spectrum. The radiation from dust thus reveals not only the presence of dust but also its environment, telling us whether it resides in sheltered molecular clouds or in the harsh glare of stellar radiation fields. Dust at 100 Kelvin emits strongly in the mid-infrared. Dust at 1000 Kelvin emits in the near-infrared and visible light. The color of dust's infrared emission thus reveals its temperature, which in turn reveals the radiation field to which it is exposed. Extended red emission in some nebulae is thought to come from certain dust components. In some emission, nebulae, astronomers observe a peculiar type of emission, a broad red or near-infrared glow that does not correspond to the standard emission lines of atoms and molecules. This extended red emission, or ERE, remains something of a mystery, but leading theories attribute it to fluorescence of certain dust components, likely including PAH molecules and other organic materials. When ultraviolet light excites these molecules, raising their electrons to higher energy states, they emit red light as the electrons return to lower energy states. This red light, when observed from many molecules simultaneously, creates the extended red glow observed in these nebulae. Diffuse interstellar bands, mysterious absorption lines in the spectra of stars, are likely linked to complex carbonaceous carriers, possibly dust-related. Some of the most persistent mysteries in astronomy involve features called diffuse interstellar bands, or DIBS. These are narrow absorption features visible in the spectra of stars viewed through interstellar dust. There are hundreds of these features, occurring at specific wavelengths throughout the visible and near-infrared spectrum. They do not correspond to any known atomic or molecular transitions in the gas phase. Their origins remain unknown, though many hypotheses attribute them to large organic molecules, possibly PAHs or other carbonaceous compounds, bound to dust grains or floating freely in interstellar space. Some of these mysterious features have been tentatively identified with specific molecules, but most remain unidentified, serving as reminders of how much we still do not understand about interstellar dust and its chemistry. Segment 6: Dust grain sizes and shapes. The universe is not composed of uniform, identical particles. Dust grains vary dramatically in size, from clusters of just a few molecules to particles containing billions of atoms. Each size of grain plays a different role in determining how dust affects light and how it participates in the cosmic environment. The distribution of grain sizes is as important as the average size, more so in many respects. Dust spans a range of sizes from molecules to submicron particles and beyond. At the smallest scale, PAH molecules are individual organic molecules containing dozens or hundreds of atoms. These smallest objects that can reasonably be called dust have sizes around 1 nanometer. Scarcely larger are small dust grains, ranging from a few nanometers to tens of nanometers across. Then come larger grains, particles that are hundreds of nanometers in size, approaching a micrometer. And finally, the largest dust grains can exceed a micrometer in size, approaching the wavelength of visible light and occasionally reaching sizes of several micrometers. The largest dust particles commonly discussed by astronomers are perhaps 10 micrometers in size, though occasionally larger aggregates are mentioned. A common picture includes large grains, small grains, and patch-sized particles. Rather than describing dust as a continuous distribution of all possible sizes, astronomers often describe dust using broad categories. There are large grains which dominate the mass of dust but are relatively few in number. A large grain might contain 1 billion times more atoms than a small grain, yet the galaxy might contain 1 billion times more small grains than large grains. There are small grains, vastly more numerous but containing little total mass. And there are patch-sized particles, the smallest objects that can properly be called dust, numerous beyond counting yet contributing little mass. Each category plays its own role. The mass distribution is dominated by large grains. The number distribution is dominated by small grains. The optical properties are distributed across all sizes, with each size range contributing to different parts of the spectrum. Large grains dominate optical extinction and far infrared emission. When starlight passes through dust, the dimming of visible light is primarily due to large grains. Large grains are more effective at scattering visible light than small grains are. Similarly, when dust in the coldest regions of space emits far infrared light, much of that emission comes from large dust grains that have been warmed slightly by background radiation. Large grains, despite being fewer in number, exert disproportionate influence on the optical and far infrared properties of dust. This makes sense physically. A single large grain occupies a cross-sectional area comparable to 1 million small grains combined. Thus, one large grain can scatter or absorb as much light as many small grains. Smaller grains contribute significantly at ultraviolet and mid-infrared wavelengths. Small dust grains are effective at interacting with ultraviolet light, producing the ultraviolet extinction and the ultraviolet bump in extinction curves. They are also responsible for much of the mid-infrared emission, the distinctive infrared signature of warm dust. The contribution of small grains becomes relatively more important at shorter and mid-infrared wavelengths. This is because small grains have larger surface areas relative to their volume, and thus interact more effectively with shorter wavelength light. Additionally, small grains can reach higher temperatures when exposed to ultraviolet light, and thus emit more strongly in the mid-infrared. Grains are not perfect spheres. Many are thought to be elongated or irregular. If we could somehow magnify a dust grain to visible size and examine it, we would not see perfect spheres. Instead, we would likely observe irregular shapes, elongated particles, and bumpy surfaces. Some grains might be nearly spherical, while others are distinctly elongated, perhaps as much as 10 times longer in one dimension than another. Some might be branching like snowflakes, or filled with cracks and crevices like cosmic sponges. This variety of shapes reflects the varied processes by which grains form and the diverse environments through which they travel. A grain that condensed in a stellar wind might be compact and nearly spherical. A grain that has undergone coagulation with other grains might be irregular and fluffy. A grain that has been processed by ultraviolet light and cosmic rays might have a pitted, cratered surface. Non-spherical grains can align with magnetic fields, affecting polarization. Magnetic fields permeate interstellar space, though they are extremely weak by terrestrial standards, perhaps 1/1,000,000th the strength of Earth's magnetic field. Elongated dust grains, by a process not fully understood but likely involving interactions with magnetic fields and radiation pressure, tend to align themselves with the direction of these magnetic fields. When aligned, elongated grains behave differently in terms of how they absorb and scatter light compared to randomly oriented grains. They absorb more light polarized in one direction than perpendicular to that direction. This property of aligned grains is crucial for creating polarized light from unpolarized starlight. Observed polarization of starlight suggests widespread grain alignment. When astronomers observe starlight that has passed through regions of dust, they often find that the light is partially polarized. This means that the light's electric field oscillates preferentially in one direction rather than in all directions equally. This polarization reveals the presence of aligned dust grains. The widespread detection of starlight polarization across many regions of the sky indicates that aligned dust is a common feature of the interstellar medium. In some regions, the polarization is as high as 5 to 10%, indicating substantial grain alignment. In other regions, polarization is barely detectable, suggesting weaker alignment or smaller grain sizes. Aligned grains preferentially extinguish certain polarization directions of light. Imagine light oscillating in a direction parallel to aligned grain's long axis. Such light interacts strongly with the grain, being absorbed or scattered readily, because the electric field of the light is aligned with the long axis of the grain. Now imagine light oscillating perpendicular to the grain's long axis. This light interacts less effectively with the grain, because the electric field is misaligned with the grain's dimensions. The result is that one polarization direction is preferentially absorbed, while the perpendicular direction is less affected. This effect creates polarization in what was originally unpolarized starlight. If all dust grains are aligned in the same direction, the resulting polarized light reveals that alignment. Polarization measurements help infer grain shapes and magnetic field orientations. The degree and direction of polarization of starlight carries information. The amount of polarization depends on the degree to which grains are aligned and the asymmetry of the grains. More elongated grains produce more polarization when aligned. The direction of polarization correlates with the direction of the magnetic field. By measuring the polarization of many stars in a region, astronomers can map the magnetic field structure and gain insights into grain shapes and sizes. Polarization measurements reveal that magnetic fields in spiral galaxies are well organized, aligned with the spiral arms. In galactic nuclei and disturbed galaxies, magnetic fields are more turbulent and chaotic. Grain size distributions evolve as grains are destroyed or grow in different environments. The distribution of grain sizes is not static or universal. In environments where grains collide and fragment, the grain size distribution shifts towards smaller sizes. Each collision can break a large grain into many small fragments. In dense clouds where grains stick together during collisions, the distribution shifts toward larger sizes. Grains accumulate into aggregates and larger structures. In regions where grains are being destroyed by shocks and radiation, the population of large grains diminishes and the distribution becomes weighted towards smaller sizes. The grain size distribution thus serves as a signature of the environment through which the dust has passed, a record written in particle sizes. Astronomers measure grain size distributions using various techniques and find that the distribution varies from place to place, reflecting the diverse environments dust encounters. Segment 7. Dust in diverse cosmic environments. Facts 71 to 80. The interstellar medium is not uniform. From place to place, it varies dramatically in temperature, density, and radiation environment. Some regions are hot and diffuse, containing only a few atoms per cubic centimeter. Others are cold and dense, containing so much gas and dust that visible light cannot penetrate. Dust in these varied environments exists in very different states, modified by the conditions surrounding it. Understanding how dust changes from environment to environment is crucial to understanding dust's role in the cosmos. In diffuse interstellar gas, dust is bare or lightly coated with mantles. In the lower density regions between molecular clouds, ultraviolet radiation from stars can penetrate easily. This ultraviolet light heats the dust and prevents volatile materials from accumulating on grain surfaces. The dust in these regions therefore tends to be simple, consisting of bare mineral grains or grains with only light coatings of material. These bare grains are relatively small and simple in composition. They have experienced less processing and accumulation than dust in denser regions. The extinction produced by dust in diffuse regions tends to be relatively shallow, with less structure in the extinction curve. In dense molecular clouds, grains often acquire thick, icy mantles. Deep within molecular clouds, where densities are millions or billions of times greater than in diffuse regions, the conditions are dramatically different. Ultraviolet light is scarce, blocked by the overlying layers of gas and dust. Temperatures plunge to tens of degrees above absolute zero. In such conditions, molecules that are gaseous in warmer environments condense into solids. These frozen materials coat the dust grains, building up layers of ice that might be thousands of molecular layers thick. If we could magnify a dust grain and its ice mantle to human size, the mantle might appear as a layer several centimeters thick, covering a hard inner core. The accumulation of ices transforms the grain completely, making it darker and more opaque. Ultraviolet radiation is weaker deep inside clouds, allowing ices to accumulate. This statement encompasses a fundamental principle of the icy mantles of dense clouds. In regions exposed to ultraviolet light, such ices would quickly vaporize, decompose, or photochemically react. But in the protected darkness of molecular cloud interiors, far from any stars, ultraviolet radiation is essentially absent. The cosmic rays that can penetrate the cloud provide some energy for chemistry, but not enough to destroy the ices. Ultraviolet radiation diminishes as it penetrates into the cloud, decreasing roughly exponentially with depth. By the time the radiation has penetrated deep enough for temperatures to drop below 100 Kelvin, the ultraviolet flux has diminished by many orders of magnitude. In this sanctuary of darkness and cold, ices accumulate steadily, year after year, building up grain mantles. Dust in H2 regions near hot stars is more heavily processed and can be partially destroyed. Not all stellar environments are conducive to dust preservation. Regions surrounding hot young stars, called H2 regions, because the intense ultraviolet radiation ionizes hydrogen gas, are harsh places for dust. Intense ultraviolet radiation heats dust grains to high temperatures, potentially sublimating their icy mantles. The radiation also drives photochemical reactions that alter grain composition. Shock waves from stellar winds blow dust grains around at high speeds, subjecting them to impacts with gas particles that can erode them. The ultraviolet radiation can also break chemical bonds in dust grain materials, making them more fragile. As a result, dust in H2 regions often shows evidence of processing. icy mantles are stripped away. Grains become smaller. The extinction curve changes, becoming flatter with less ultraviolet extinction. Shock waves from supernovae can shatter grains into smaller fragments. The most violent events in the universe are supernova explosions. When one of these occurs, the expanding blast wave rushes outward at speeds of tens of thousands of kilometers per second. When this shock wave encounters dust, the consequences are catastrophic. Dust grains collide with gas particles accelerated by the shock, experiencing impacts of tremendous violence. The relative velocity between grain and gas can exceed thousands of kilometers per second. At these speeds, the impact vaporizes the grain, or at minimum, shatters it into tiny fragments. Many grains are shattered into tiny fragments that scatter in all directions. Others are vaporized entirely. Their atoms return to the gas. The shock passing through a dusty region thus transforms the grain size distribution dramatically, shifting it towards smaller grains. Observations of dust in supernova remnants often show evidence of grain destruction and shattering. In calm regions, grains may coagulate, sticking together to form larger aggregates. In regions where shock waves are absent and velocities are low, dust grains move slowly relative to one another. Relative velocities are perhaps 1 centimeter per second or less. When grains do collide at such low velocities, the collision is gentle. Adhesive forces arising from van der Waals interactions, weak electromagnetic attractions between atoms, and electrostatic effects can cause the colliding grains to stick together. Over time, individual grains accumulate to form larger aggregates, clumps of many grains bonded together. This coagulation process is crucial in planetary formation, where dust aggregates eventually grow into pebbles, planetesimals, and planets. In molecular clouds and around young stars, coagulation is a significant process, increasing the average grain size over millions of years. Icy mantles and coagulation make grains in dense clouds more fluffy and porous. Grains that have accumulated thick icy mantles and have coagulated with other grains form structures quite different from bare mineral grains. These fluffy, porous particles contain numerous cracks, crevices, and empty spaces. Their density is much lower than compact mineral grains would be. Imagine the difference between a ball of tightly packed iron and a loosely connected clump of marshmallows, and you begin to grasp the structural difference between compact grains and fluffy coagulated aggregates. These fluffy structures have profound implications for how they interact with light and other material. They are more opaque than compact grains of the same total mass because the light encounters multiple surfaces and interfaces rather than scattering from a single grain. They are more fragile, more easily broken apart by collisions. Dust properties can differ between the galactic disk, halo, and central regions. Our Milky Way galaxy has a structure, a flattened disk where most of the stars and gas reside, a spherical halo of older stars extending far above and below the disk, and a central bulge around the supermassive black hole at the galaxy's core. The dust in these different regions has experienced different histories and resides in different environments. The dust of the disk, where star formation is active, where young stars inject energy and radiation, differs significantly from the dust of the halo, where stars are mostly old and relatively inactive. The dust of the disk shows evidence of recent processing by stellar radiation and supernovae. The dust of the halo is older, less processed, smaller on average. The central bulge, with its high stellar density and intense radiation fields from the galactic nucleus, hosts dust unlike that found elsewhere in the galaxy. The dust in the central region is more heavily processed, more heavily depleted of ices. Metal-poor environments in early galaxies likely had different dust compositions. When the universe was young, shortly after the Big Bang, stars had not yet synthesized significant amounts of metals, the heavy elements. The early generations of stars were composed almost entirely of hydrogen and helium. In these metal-poor galaxies, the dust could not have the same composition as dust in our modern metal-rich galaxy. The proportion of silicate dust, which depends on the availability of silicon, iron and magnesium, would have been different. Early galaxies would have had more of the carbon-based dust, since carbon is produced earlier in stellar evolution than metals like iron and magnesium. The overall dust population would have been less abundant, since there had been fewer stellar generations to produce dust. The extinction curves of early universe galaxies would have been different, with different ratios of ultraviolet to visible extinction. Over cosmic time, dust content in galaxies has grown as successive stellar generations enrich the medium. This is one of the grand stories of cosmic evolution. Early galaxies, poor in metals and in dust, gradually accumulated more and more of both as stars formed, fused new elements, and died. Each generation of stars added fresh metals and dust to the galaxy. Over billions of years, galaxies became progressively enriched. Modern galaxies, like our Milky Way, are the product of this long cosmic enrichment, now rich in metals and dust after 12 billion years of stellar alchemy. The dust abundance in the universe has increased dramatically since the Big Bang, growing from essentially zero in the earliest galaxies to substantial amounts in modern galaxies. This enrichment of the universe with dust is one of the most important processes in galactic evolution. Segment 8. The chemistry of dust. Dust is not merely a spectator in the cosmos. It is not simply a passive material that scatters light and emits infrared radiation. Rather, dust plays an active role in the chemistry of the universe, providing surfaces where chemical reactions occur and influencing how the universe's chemistry unfolds. Without dust, the chemistry of space would be fundamentally different, and life as we know it would be impossible. Dust grains provide surfaces where atoms and molecules can meet and react. In the gas phase of interstellar space, atoms and molecules move freely, traveling great distances before encountering one another. The density of the interstellar gas is so low that collisions are rare. A molecule in a typical diffuse cloud might travel thousands of kilometers before encountering another molecule in a way that allows a chemical reaction. The volume is so large, the distances so vast, that encounters are extremely rare. But dust grains provide an alternative stage for chemistry. Atoms and molecules can land on a grain surface, becoming temporarily stuck through weak van der Waals forces, electromagnetic attractions between atoms that are much weaker than chemical bonds. While on the surface, they can move around, occasionally encountering other atoms or molecules. When they do, reactions become possible. The dust surface thus acts as a gathering place, a marketplace where atoms meet and react. Hydrogen molecules form efficiently on dust surfaces in cold clouds. One of the most important molecules in the universe is hydrogen, H2, two hydrogen atoms bonded together. Hydrogen molecules are found everywhere in space, in diffuse clouds, in molecular clouds, and in the atmospheres of stars and planets. Yet, despite its abundance and importance, molecular hydrogen does not form efficiently in the gas phase of space. In the cold, diffuse interstellar medium, the reaction that creates H2 from two hydrogen atoms is extremely slow. The atoms have very little thermal energy, and collisions that might lead to bonding are rare. The presence of dust changes this entirely. A hydrogen atom landing on a dust grain surface can stick to the surface through van der Waals forces. When another hydrogen atom lands nearby, they can react, bonding together to form H2. This happens because the dust surface constrains the hydrogen atoms, keeping them close together long enough for the chemical bond to form. Without dust, H2 formation in space would be far less efficient. This statement underscores the crucial role dust plays. Computer models of the early universe that ignore dust predict far less molecular hydrogen than is actually observed. Models that account for dust using realistic dust abundances and properties produce the observed abundances of H2. This suggests that throughout cosmic history, dust has been essential for the formation of hydrogen molecules. Without dust, the universe would be a very different place, lacking molecular hydrogen and the molecules that build upon it. The molecular clouds that are the birthplaces of stars would not form, or would form much less readily. The chemistry of the universe would be impoverished. Icy mantles host reactions that build increasingly complex molecules. Water ice covers dust grains in cold molecular clouds. On the surfaces of these ice-covered grains, chemistry occurs. Simple molecules can interact with one another on the ice surface, forming more complex molecules. A hydroxyl radical, OH, can react with a carbon monoxide molecule to form formaldehyde, H2CO. Formaldehyde can react with other species to form even more complex molecules. Over time, on the surfaces of ice-covered dust grains, organic molecules of increasing complexity build up. Starting with simple molecules like carbon monoxide, water, ammonia, and methane. Dust grain surfaces catalyze the formation of more complex molecules like alcohols, aldehydes, and organic acids. Eventually, molecules of tremendous complexity can form, molecules with dozens or even hundreds of atoms. Complex organic molecules that rival the complexity of biological molecules. Ultraviolet photons and cosmic rays can drive chemistry within these ices. Ice-covered grains are protected from most ultraviolet light by the overlying layers of gas and dust. Yet cosmic rays, particles of enormous energy, created in supernova explosions and other violent events, can penetrate the cloud, striking ice-covered grains directly. These cosmic rays deposit energy in the ices, breaking chemical bonds and creating reactive species, free radicals with unpaired electrons. These reactive species then participate in chemical reactions, leading to the synthesis of new molecules. Additionally, ultraviolet light from cosmic background radiation and photons from starlight that penetrate into the outer layers of clouds can energize chemical reactions. Chemistry in interstellar ices is thus driven by both cosmic rays and photons, with cosmic rays being more important in the deepest, most shielded regions. When ices are heated or desorbed, complex organic molecules can be released into the gas. As a molecular cloud begins to form a star, the region around the forming star heats up. Infrared radiation from the young star penetrates the surrounding dust cloud, heating the dust and the ices on the grain surfaces. As temperatures rise above 50 Kelvin, ices begin to vaporize or desorb, returning to the gas phase. As they do, the complex organic molecules that were created in the solid state are released. These molecules then become part of the gas that surrounds the young star, potentially becoming incorporated into planets. Complex organic molecules created on dust grain surfaces in cold molecular clouds can thus seed planetary systems, providing the chemical building blocks for planets. It is possible that some of these dust-produced molecules ended up in our solar system, incorporated into the planets and moons that orbit our Sun. Dust therefore contributes to the chemical richness of star-forming regions. Without dust as a substrate for chemical reactions, and without the complex molecules formed on dust surfaces, star-forming regions would have less chemical diversity. The ices that build up on dust in molecular clouds and the organic molecules synthesized on grain surfaces add chemical richness to the environments where stars and planets form. This chemistry, occurring on dust grains, thus influences the chemical composition of newly formed stars and planets. A protoplanetary disk forming around a young star inherits the chemical complexity created by dust grain surface chemistry in the parent molecular cloud. Some prebiotic molecules likely originate from dust grain surface chemistry. Prebiotic molecules are molecules thought to have been necessary for the origin of life. They include amino acids, nucleotides, and other organic compounds. Some scientists argue that some of these molecules or their precursors were synthesized on dust grain surfaces in interstellar space or in meteorites that fell to the early Earth. The chemistry of dust could thus have had a role in making life possible. Though this remains speculative, the chemical complexity that dust can generate suggests it played some role in the chemical origins of life. Meteorites that fell to Earth in its early history contained complex organic molecules, some of which may have originated in dust chemistry. These compounds may have served as starting points for prebiotic chemistry. Gas-ice exchanges influence how energy and radiation travel through molecular clouds. Dust and ices are not passive components of molecular clouds. They actively influence how radiation propagates through the cloud. Dust absorbs ultraviolet and visible light, preventing these wavelengths from penetrating deeply. Dust re-radiates absorbed energy as infrared light. This affects the radiation environment deep within clouds, reducing ultraviolet flux but enhancing infrared radiation. Similarly, ices on grain surfaces can absorb and emit radiation, further modifying the radiation environment. These exchanges between gas and ice alter the energy balance of molecular clouds, affecting temperatures and the rates of chemical reactions. In a dense cloud, the radiation environment is dominated by infrared light, while in diffuse regions, visible and ultraviolet light penetrate more readily. The presence of dust changes the cooling rates and thermal balance of interstellar gas. The temperature of interstellar gas depends on a balance between heating and cooling. Dust plays a crucial role on both sides of this balance. When ultraviolet light is absorbed by dust, The energy can be transferred to gas through collisions, heating it. When gas cools by emitting radiation, dust can carry away much of the radiated energy, accelerating the cooling. The presence of dust thus affects both the heating and cooling rates of interstellar gas, ultimately determining the temperature and thermal structure of the interstellar medium. In regions with abundant dust, cooling is efficient and temperatures remain low. In dust-poor regions, cooling is less efficient and temperatures are higher. The temperature structure of the interstellar medium is thus intimately connected to dust. Segment 9. Dust and the birth of stars. Stars are not born fully formed in the void of space. Their births are processes of gradual growth, preceded by long periods of gravitational collapse within clouds of gas and dust. Dust plays a crucial role in these births, acting as a catalyst for the very processes that create stars. Without dust, stars would form far less readily, and the universe would contain far fewer stars. The cosmic fate of galaxies is shaped by the role dust plays in star formation. Dust helps clouds cool, an essential step for gravitational collapse. A cloud of gas in space is subject to the force of gravity, pulling its particles inward. Yet gravity is opposed by the pressure of the gas, the random thermal motion of particles pushing outward. For a cloud to collapse under gravity, gravity must overcome this pressure. For gravity to overcome pressure, the cloud must be cold. Dust assists in cooling the cloud by radiating away thermal energy. Dust absorbs ultraviolet and visible light and re-radiates that energy as infrared light. This infrared radiation escapes from the cloud, carrying away energy and cooling the gas. Without dust's role in cooling, clouds would remain warm and resist gravitational collapse. Cold clouds are essential for star formation. The temperature determines the critical mass at which a cloud fragment becomes gravitationally unstable and collapses. A hot cloud requires much more mass to collapse than a cool cloud. By radiating away energy, dust allows gas to contract and form stars more easily. This is a direct consequence of dust's role in cooling. With dust present, clouds can cool efficiently. Cool clouds collapse more readily. The collapse leads to star formation. Without dust, clouds would be hotter, would resist collapse, and would form fewer or no stars. The existence of stars throughout the universe thus depends, in an important sense, on dust's cooling properties. Early galaxies in the young universe were less dusty than modern galaxies. As a result, they formed stars less readily and had different star formation rates. As galaxies accumulated dust over billions of years, their ability to form stars changed. The dust abundance in galaxies is thus intimately connected to the cosmic star formation history. Dust shields interior regions of clouds from harsh ultraviolet radiation. The interior regions of molecular clouds are often shielded from external ultraviolet radiation by layers of gas and dust at the cloud surface. This is crucial because ultraviolet radiation would destroy the fragile molecules that exist in the cloud's interior. Ultraviolet photons carry enough energy to break chemical bonds, decomposing molecules back into atoms. Dust provides this shield, absorbing the ultraviolet photons before they can penetrate deeply, protecting the molecules within. In the depths of a molecular cloud, shielded by layers of dust, ultraviolet intensity is reduced by many orders of magnitude. This allows fragile molecules to persist and for complex chemistry to unfold. This shielding protects fragile molecules and promotes further chemical complexity. In the protected interior of dust-shielded clouds, delicate molecules can persist. Molecules like carbon monoxide and more complex carbon-containing compounds, which would be readily destroyed by ultraviolet light, survive indefinitely. More than this, in these protected regions, chemistry proceeds at its own pace, allowing molecules of increasing complexity to form. The molecular richness of star-forming regions owes much to the dust that shields them from external ultraviolet light. Different molecules form in different temperatures and densities, creating chemical gradients within clouds. The richest chemistry often occurs in the regions most protected from ultraviolet light. Dense cores within dusty clouds are the birthplaces of new stars. Not all parts of a molecular cloud form stars equally. Rather, denser regions within the cloud, called dense cores, are where star formation initiates. Dense cores are regions where the density of gas and dust exceeds the surrounding cloud by a significant factor, sometimes by orders of magnitude. Within these cores, gravity is especially strong, overwhelming pressure, driving rapid collapse. It is within these dense cores, regions of high dust concentration, that stars are born. Dense cores form when gravity amplifies small density variations in clouds, pulling more material into already dense regions. Once a dense core forms, it becomes unstable to further collapse, and gravitational runaway begins. Dust opacity limits how deeply visible light can penetrate into star-forming regions. Dust is opaque. It blocks light. Regions of high dust density are therefore invisible to ordinary telescopes observing invisible light. The denser the dust, the deeper the opacity, and the less visible light escapes. This means that the regions where stars are actively forming, which tend to be the densest regions rich in dust, are hidden from visible observation. They appear as dark patches against the light of background stars. Astronomers call these regions dark clouds or dark nebulae. To observe the hidden regions of star formation, we must use other wavelengths of light. Infrared and radio observations are used to peer through dense, dusty envelopes. To observe the hidden regions of star formation, astronomers must employ different wavelengths. Infrared light penetrates dust more readily than visible light, allowing observation of dusty regions. Radio and submillimeter radiation penetrates even more deeply, reaching through dust clouds that are completely opaque in visible light. Using infrared and radio telescopes, astronomers can peer through dust that completely blocks visible light, observing the regions where stars are being born. Young protostars, still surrounded by substantial dust, glow brightly in infrared as they are heated by gravitational contraction. Radio observations reveal the molecular gas surrounding the protostars. Together, infrared and radio observations paint a complete picture of star formation hidden from optical view. The earliest stages of star and planet formation are largely hidden by dust. The earliest, most dramatic stages of star and planet formation are obscured by dust. Young protostars are surrounded by disks of gas and dust from which planets will eventually form. These disks are opaque in visible light. The accretion of material onto the protostar releases gravitational energy as heat, but much of this heat is radiated as infrared light, which can be detected through dust. Only through infrared and submillimeter observations can we study the processes of star and planet formation as they occur. The most vigorous, most important phases of stellar and planetary growth are hidden from optical view. Dust grains in protoplanetary disks are the building blocks of planets. Around young stars, before the star has settled into a stable state, its surrounding disk of gas and dust is actively evolving. The dust in this disk, the same cosmic dust we have been discussing, serves a new role. It is the material from which planets will be built. Dust grains, ranging from microns to larger particles, collide with one another in the disk. When they collide gently, they stick together through van der Waals forces and electrostatic attraction. Over time, dust grains accumulate into larger and larger aggregates. This is the beginning of planet formation, the slow accumulation of dust into worlds. Collisions and sticking among dust grains initiate the growth from micron-sized particles to pebbles and beyond. The process of planetary growth begins with dust. Two dust grains collide and stick, forming a two-grain aggregate. This aggregate collides with other dust grains, growing to 3 grains, 10 grains, 100 grains. As the aggregate grows larger, it becomes a pebble, then a larger rock. The growth is initiated and driven by the collision and sticking of microscopic dust grains. Without this initial sticking, planetary growth could never commence. The sticking of dust grains is thus one of the most fundamental processes in the universe, the process that makes planets possible. Over time, dust aggregates grow into planetesimals and then into full planets. The growth of dust into planets does not occur instantaneously. Rather, it is a gradual process that unfolds over millions of years. Dust grains stick together to form larger aggregates. These aggregates grow, becoming pebbles, then larger rocks. At some point, the accumulation of mass reaches a threshold. Gravity becomes strong enough to significantly accelerate the growth. The largest bodies in the disk gravitationally attract material from their surroundings, growing ever larger. Through this process, planetesimals, rocky bodies kilometers in size, form. Planetesimals continue to collide and accumulate, eventually growing into planet-sized bodies. The process is slow at first, then accelerates dramatically as bodies grow large enough for their gravity to dominate. The composition of planetary surfaces reflects the dust mixture in the original disk. The dust in a young planetary disk is not uniform. In regions closer to the star, temperatures are higher. In regions farther from the star, temperatures are lower. Dust with different compositions has different properties, including different volatilities, the tendency to evaporate at certain temperatures. Icy dust, composed partly of frozen materials like water ice and methane, cannot survive in the hot inner regions of disks. It vaporizes, returning to the gas phase. Only rock and metal dust survives in the inner regions. Farther out, where it is colder, icy dust survives and accumulates. As dust accumulates into planets, the composition of each planet reflects the dust composition in the disk region where the planet formed. Planets formed from rocky dust in the inner solar system have silicate surfaces and iron cores. Planets formed from icy dust farther out, like Jupiter, contain substantial frozen materials. The composition of planets thus bears the signature of the dust from which they were assembled. ice-rich grains beyond the snowline contribute to the formation of icy moons and comets. In every planetary system, there is a distance from the star called the snowline, beyond which it is cold enough for water ice and other volatile ices to persist in solid form. In the region beyond the snowline, dust accumulations include substantial quantities of ice. When planets form beyond the snowline, they incorporate this ice into their structure. Large planets that form beyond the snowline, like Jupiter, accumulate substantial ices, which help them achieve rapid growth by adding to their mass. Moons that orbit these planets and comets that populate the outer solar system are rich in ice because they formed from ice-rich dust beyond the snowline. In our own solar system, the icy moons of the outer planets and the comets of the Oort cloud are remnants of the ice-rich dust that existed in the outer solar system billions of years ago. Dust distribution within disks shapes where different types of planets can form. The way dust is distributed in a disk is not random. In some regions, dust concentrates more densely than in others. This uneven distribution affects where planets form and what types of planets form. Denser regions of dust accumulate into larger planets more readily. Regions depleted in dust form fewer or smaller planets. The underlying dust distribution pattern thus acts like a template, determining where planetary formation will be most vigorous and what planet masses will result. Observations show that protoplanetary disks often have non-uniform dust distributions, with regions of enhanced dust density separated by gaps. These patterns shape the planetary systems that eventually form. Dust rings and gaps observed in disks hint at emerging planets sculpting the material. Modern observations of nearby protoplanetary disks made with instruments like the Atacama Large Millimeter Array reveal a striking feature. Many disks contain rings of concentrated dust separated by gaps nearly devoid of dust. These patterns are thought to be caused by planets forming within the disk. A growing planet, with its gravitational influence, clears a gap in the disk by scattering particles away from its orbital path. Material piles up at the edges of the gap, forming rings of concentrated dust. The patterns of rings and gaps observed in disks thus represent snapshots of planet formation in action, revealing the presence of planets still too small or too faint to observe directly. These observations have revolutionized our understanding of how planets form, showing that planets are not formed fully grown, but rather grow gradually, sculpting the dust disk around them. Segment 10. Dust in mature planetary systems. Planetesimal impacts grind solids back into dust, sustaining debris disks around some stars. Star formation and planetary formation are not the only contexts where dust appears. Around many mature stars, even old stars like our Sun, dust reappears in the form of debris disks. These disks are different from the protoplanetary disks that surround young stars. In debris disks, the planets have already formed and settled into stable orbits. Yet in these planetary systems, collisions continue to occur. Planetesimals that escaped incorporation into planets collide with each other and with planets, generating impacts that grind solids back into dust. This dust, called debris dust, orbits the star, creating the debris disk observed around the star. Our own solar system contains a debris disk, the Kuiper belt, populated with icy objects and dust. Asteroid collisions in the inner solar system create additional dust. Dust in young systems thus cycles between small grains and larger bodies. In young planetary systems, dust is constantly recycled. Dust grains collide and accumulate into larger bodies. Larger bodies collide and fragment into dust again. This cycling between dust and larger objects continues throughout the development of a planetary system. The cycling is most vigorous in young systems, where impacts are frequent and violent. As the system ages, the cycling slows and eventually stops. Young systems with ages of millions of years show vigorous dust cycling. Older systems with ages of billions of years have calmer dust populations. In older systems, dust levels drop as material is locked into planets or cleared. As a planetary system ages, dust becomes less abundant. Some of the dust that remains is gradually removed from the system. Radiation pressure from the host star pushes small grains outward and away from the star. Eventually, these grains are either lost to interstellar space or dragged inward and destroyed. Meanwhile, dust that collides with planets is incorporated into them, or if it falls toward the star, is vaporized. The result is that old planetary systems like our own solar system have much less dust than young systems. Our solar system contains far less dust now than it did 4 billion years ago. The dust disk around the Sun is now much thinner and more tenuous than it was in the early solar system. Observations of dust in other systems give clues to how our own solar system formed. Our solar system is ancient, 4.6 billion years old. The evidence of its origin, the dust and planetesimals from which planets formed, has been largely erased by time. Yet around other stars, we observe young planetary systems with configurations similar to our own. These young systems still contain dust, still have detectable remnants of planet formation. By studying dust in these young systems, we gain insights into what our own solar system must have been like in its youth. Dust observations thus provide a window into our cosmic history. Young solar system analogues can be found at various stages of evolution, allowing us to piece together the history of our own solar system by observing similar systems at different ages. Dust therefore connects the scales from molecules to entire planetary systems. Dust serves as a bridge connecting vastly different scales of the cosmos. At the small scale, dust grains consist of or are coated with molecules, organic compounds of remarkable complexity. At intermediate scales, dust accumulates into asteroids and planetesimals. At the largest scales, planets form from dust. A single concept, dust, encompasses scales ranging from billionths of a meter to billions of meters. This remarkable range, all encompassed within the physics of interstellar and circumstellar dust, demonstrates the deep unity of the cosmos. The same physical processes that govern dust-grain interactions also govern planetary formation and the structure of galaxies. Segment 11. Observing Dust, Methods and Mysteries. How do astronomers know about dust that is often too small to be seen even with the most powerful telescopes? The answer lies in cleverness and ingenuity. Astronomers cannot directly observe most dust grains, but they can observe the effects that dust produces. By carefully analyzing these effects, they can infer the properties of dust with remarkable accuracy. This indirect approach has proven surprisingly powerful, revealing details about dust that direct observation would never uncover. Astronomers infer dust properties through its effects on light and its own emission. This is the fundamental observational approach. Dust reveals its presence not by being seen, but by how it affects the light that passes through it and by the light it emits. By analyzing extinction, reddening, and infrared emission, astronomers can determine dust abundance and properties with remarkable precision. The universe, though vast and distant, communicates with us through the light it sends. Dust is one of the speakers in this cosmic conversation. Extinction and reddening of background stars reveal how much dust lies along a line of sight. When astronomers observe a star through dust, they see a dimmer, redder image than they would see if no dust were present. By comparing the observed dimming to the observed reddening, they can calculate the dust abundance along the line of sight. This technique works because the relationship between extinction and reddening depends on the dust grain properties. Different dust compositions produce different extinction to reddening ratios. By measuring this ratio, astronomers can not only determine dust abundance, but also infer something about dust properties. Stars are used as natural probes, their light serving as diagnostics for the dust that obscures them. Polarization measurements trace grain alignment and magnetic fields. The polarization of starlight, as discussed earlier, provides information about dust grain shapes and magnetic field orientations. By measuring the degree and direction of polarization for many stars, astronomers can create maps of magnetic field structure. The amount of polarization depends on grain sizes and the degree of alignment. By analyzing polarization data carefully, astronomers can infer the properties of the dust that causes the polarization. Magnetic fields, invisible to our eyes, are revealed by their effects on dust. Dust becomes a tracer of magnetic structure, mapping fields that would otherwise be undetectable. Infrared spectroscopy identifies vibrational features of silicates and hydrocarbons. When infrared light is spread into a spectrum, showing intensity as a function of wavelength, distinctive absorption and emission features appear. Silicate grains produce characteristic absorption features at specific wavelengths. Carbonaceous dust produces different features at different wavelengths. Water ice produces its own signature. By analyzing infrared spectra with high wavelength resolution, astronomers can identify the specific types of dust present in a region. This technique has proven invaluable for understanding dust composition. Telescopes in space, operating above Earth's atmosphere, can detect infrared light with exquisite detail, revealing the composition of dust in regions across our galaxy and in distant galaxies. Ultraviolet observations capture the characteristic 217.5 nanometer bump and far ultraviolet rise. Ultraviolet light, beyond the range of human vision, reveals features in dust that are not visible to optical telescopes. The distinctive ultraviolet bump is a hallmark of galactic dust. Beyond this bump, the extinction continues to rise at shorter wavelengths, extending into the far ultraviolet. This rise provides additional constraints on dust properties, particularly the sizes and compositions of small grains. Far ultraviolet observations require space telescopes as Earth's atmosphere absorbs ultraviolet light. Satellites observing in the ultraviolet have provided crucial data on dust in our galaxy. Space telescopes like JWST and previous missions have mapped dust in our galaxy and beyond. The James Webb Space Telescope, launched in 2021, has the capability to observe infrared light with unprecedented detail, penetrating dust clouds that were opaque to previous telescopes. Earlier space telescopes, including Spitzer, Herschel, and others, have provided crucial data on dust. These space-based observatories, operating above Earth's atmosphere, can detect infrared and ultraviolet radiation that would be absorbed by the atmosphere if measured from the ground. Through their observations, they have mapped the distribution and properties of dust in our galaxy and in distant galaxies. The data from space telescopes has revolutionized our understanding of dust, revealing structures and properties that ground-based observations could not detect. Submillimeter and millimeter observatories reveal cold dust in star-forming regions. The coldest dust, residing in the depths of molecular clouds where temperatures are only tens of degrees above absolute zero, emits radiation at the longest infrared wavelengths in the submillimeter and millimeter ranges. To observe this radiation, astronomers use specialized telescopes sensitive to these wavelengths. The Atacama Large Millimeter Array, the Submillimeter Array, and other such instruments have revolutionized our ability to observe dust in star-forming regions, revealing regions of active star and planet formation that were previously invisible. These submillimeter telescopes can detect the faintest dust emission, revealing dust clouds too cold and too faint to observe invisible light. Dust emission is a key tracer of regions where new stars are forming. Star formation heats dust, causing it to emit infrared radiation. The amount of infrared emission from dust correlates with the rate at which stars are forming. By observing dust emission, astronomers can identify star-forming regions and estimate the star formation rate. Galaxies undergoing vigorous star formation are bright in infrared, dominated by the emission from heated dust. Galaxies with low star formation rates are dimmer in infrared. The infrared glow of dust thus reveals the cosmic history of star formation, showing us where and when stars formed in the universe. Large-scale maps show that dust outlines spiral arms and dense filaments in galaxies. When astronomers map the distribution of dust in galaxies using observations across many wavelengths, a beautiful pattern emerges. Dust concentrates in spiral arms, the rotating density waves that give spiral galaxies their distinctive appearance. Dust also gathers in filaments, elongated structures of enhanced density stretching across galaxies. These structures outline the major features of galactic architecture, showing how dust follows the gravitational potential wells created by stars and dark matter. Dust is not randomly distributed, but rather concentrated in structures revealed by gravity. Observations of distant galaxies rely on dust corrections to recover their true starlight. When astronomers observe distant galaxies, much of the light they detect from those galaxies is not directly from stars, but from dust that has been heated by starlight. The light is reprocessed by dust. To understand what a galaxy's true stellar population is and how rapidly it is forming stars, astronomers must account for dust. They must correct their observations for dust absorption and emission. Without these corrections, the properties of distant galaxies would be fundamentally misunderstood. Dust thus plays a crucial role even in our most distant observations, influencing how we understand the universe's structure and history. Laboratory studies create analog materials to mimic interstellar grains. Scientists in laboratories cannot directly obtain grains of interstellar dust, for the dust is separated from Earth by vast distances and is fundamentally difficult to capture. Instead, they create materials that mimic interstellar grains. They synthesize silicates similar to those thought to exist in space. They create carbonaceous materials with properties similar to cosmic carbon. These analog materials allow laboratory investigation of dust properties. Through careful experimentation, scientists can measure how these materials absorb and scatter light, how they interact with radiation, how they respond to chemical processing. Carbonaceous and silicate analogues are produced and measured across ultraviolet to infrared wavelengths. The analog materials created in laboratories are carefully characterized. Scientists measure how these materials absorb and scatter light across a wide range of wavelengths, from ultraviolet through visible to infrared. These measurements, obtained in controlled laboratory conditions, can be compared with astronomical observations. If the laboratory measurements match the astronomical data, the hypothesis that the analog material resembles real cosmic dust is supported. Scientists systematically test different compositions, creating materials with different hydrogen to carbon ratios, different degrees of crystallinity, different grain shapes. Comparing laboratory spectra with astronomical data helps identify likely grain compositions. By systematically testing different compositions and structures of analog materials and comparing the resulting spectra with observations of actual dust in space, scientists can narrow down the possible compositions of cosmic dust. Different dust compositions produce distinctive spectral features. By finding the laboratory analog that best matches astronomical observations, scientists can confidently say what the dust likely contains. This comparative approach has identified silicates, carbonaceous materials, water ice, and other compounds in interstellar dust. Experiments simulate cosmic processing through ultraviolet irradiation and ion bombardment. Dust in space is not chemically static. It undergoes processing as it is exposed to ultraviolet light and cosmic rays. To simulate these processes in the laboratory, scientists expose analog materials to ultraviolet light in a controlled manner, or bombard them with ions simulating cosmic rays. They then measure how the material properties change. This allows them to understand how dust evolves as it is processed by the radiation environment of space. Scientists have shown that ultraviolet exposure can transform carbonaceous dust, increasing its aromaticity, changing its optical properties. These studies show how dust evolves under interstellar conditions. Through laboratory simulations, scientists have shown that the composition and structure of dust can change substantially when exposed to ultraviolet light or ion bombardment. Materials that are initially aliphatic can become more aromatic. Materials that absorb light in one region of the spectrum can be transformed to absorb light at different wavelengths. These laboratory findings help explain how dust composition can change as dust travels through space and experiences different radiation environments. The universe is a giant laboratory, conducting experiments on dust at scales and temperatures we can barely reproduce in terrestrial labs. Laboratory ice analogues explore chemistry on grain mantles at low temperature. Some of the most intriguing experiments in dust science involve ices. Scientists create layers of ice similar to the icy mantles on dust grains in molecular clouds. They cool these ices to temperatures as low as 10 Kelvin, matching the conditions in cold molecular clouds. They then expose the ices to ultraviolet light or cosmic rays, simulating the radiation environment. They measure what new molecules form. These experiments have revealed that complex chemistry, including the formation of organic molecules, can occur on ice surfaces at the low temperatures of interstellar space. Scientists have detected amino acids and other prebiotic molecules forming in these experiments. Measured optical constants feed into models of dust absorption and scattering. The optical properties of materials are described by optical constants, numbers that characterize how a material absorbs and scatters light. These constants depend on wavelength. By measuring the optical constants of analog materials in the laboratory across a wide range of wavelengths, scientists obtain fundamental data needed for theoretical models. These optical constants are then used in computer models that calculate how dust affects light. The models can be compared with astronomical observations, testing whether the assumed dust composition and properties are correct. As optical constants are refined, models improve. Combining theory, experiment, and observation gradually refines dust models. Understanding dust is not the work of a single approach. It requires the interplay of theory, laboratory experiment, and astronomical observation. Theorists develop models of dust, proposing dust compositions and structures. Experimenters create analog materials and test how these materials behave under simulated cosmic conditions. Observers measure the properties of actual dust in space. When there are discrepancies between models and observations, theorists refine the models, experimenters conduct new experiments, and observers conduct new observations. Through this iterative process, understanding gradually improves. Science is a conversation between theory and reality. Multiple dust models can often reproduce broad features, leaving some ambiguities. Despite the sophistication of modern dust science, ambiguities remain. Different dust models, with different assumed compositions or grain size distributions, can often reproduce the major observational features. This is because observations are limited. We observe dust at certain wavelengths with certain instruments. Multiple models may fit the available data. To distinguish between models, new observations with different instruments or observations at new wavelengths are often needed. These ambiguities drive future research, motivating observations with new instruments and telescopes. Ongoing work aims to pin down how much of each dust component is actually present. A major effort of dust science is to constrain the absolute abundance of different dust components. How much silicate dust is present? How much carbonaceous dust? How much icy material? What fraction of carbon resides in PAHS versus in larger carbonaceous grains? What percentage of galaxies contain unusual dust that deviates from the standard composition? These questions drive much current research. As observations improve and laboratory experiments reveal more details, the answers to these questions become more precise. Over time, a detailed census of the universe's dust composition is emerging. Future missions will provide even more detailed observations. Segment 12. The evolution and destruction of dust. Dust is not eternal. Though dust persists for billions of years, traversing the galaxy multiple times over, it is not immune to change or destruction. Dust grains are constantly altered by their environments, modified by chemistry, heating, and radiation. Understanding how dust evolves and is destroyed is essential to understanding the dust population that exists at any given time, and how dust's role in the universe has changed over cosmic history. Dust grains are not permanent. They are constantly altered by their environment. This fundamental statement encompasses much of what we will discuss in this final segment. No grain of dust exists in an unchanging state. Each grain is subject to forces that modify it. These modifications are not always dramatic. In the quiet depths of molecular clouds, changes occur slowly, but change occurs nonetheless. Over cosmic time, these slow changes accumulate, transforming the nature of dust. A grain that has traveled for 1 billion years is no longer the same grain it was at the beginning of that journey. High-energy photons can break chemical bonds and modify grain surfaces. Ultraviolet light carries enough energy to break the bonds that hold atoms together in molecules. When ultraviolet photons strike dust grains, they can break bonds in the grain material, breaking molecules into fragments. They can also break bonds in icy mantles coating grains, vaporizing ices, or breaking them into simpler products. In regions with strong ultraviolet radiation fields, this photochemical processing occurs rapidly. Dust grains exposed to harsh ultraviolet light are transformed, their surfaces altered, their composition changed. A grain in a diffuse region with strong ultraviolet radiation will evolve differently from a grain in a shielded molecular cloud. Shocks from supernova remnants can sputter atoms from grains, eroding them. A supernova explosion sends a shock wave through space. When this shock strikes dust grains, it accelerates gas particles to tremendous velocities. These fast particles collide with the grains, transferring momentum and energy. In a process called sputtering, the impact of a fast gas particle can kick an atom out of a grain, removing it entirely. Over thousands of collisions, grains can be substantially eroded and diminished in size. A shock passing through a dusty region can significantly reduce the grain sizes present. Observations of dust in supernova remnants show evidence of this processing. Grain-grain collisions in shocks can shatter large grains into smaller fragments. Beyond sputtering, another destructive process occurs in shocks. Grain-grain collisions, violent collisions between dust grains accelerated to high velocities by the shock, can occur. When two large grains collide at high velocity, the impact can shatter both grains into many smaller fragments. This shattering effect, combined with sputtering and vaporization, means that shocks are highly effective at reducing grain sizes. The grain size distribution in shocked regions shifts towards smaller sizes. This has observable consequences, changing extinction curves and other dust properties. Some dust is entirely destroyed in hot gas, returning its atoms to the gas phase. In the most extreme environments, such as the hot gas surrounding young, massive stars, dust cannot survive at all. Temperatures are so high that the bonds holding atoms together in grains cannot remain intact. Grains vaporize entirely, returning to the gas phase as individual atoms and molecules. All trace of the grain structure is lost. The atoms return to the gas, available to form new grains at a later time. In some extreme environments, temperatures exceed 10,000 Kelvin, hot enough to vaporize any solid material. Yet in nearby regions, new dust may be forming, replacing what was destroyed. In calmer regions, atoms and molecules accrete back onto surviving grains. Not all environments destroy dust. In regions removed from the harsh radiation fields and shock waves, conditions favor the growth of dust. Gas molecules and atoms collide with surviving dust grains, sticking to their surfaces. Over time, material accumulates on grain surfaces, rebuilding mantles or adding to the grain's mass. This accretion can occur over millions of years, slowly adding material. In dense clouds where temperatures are low and densities are high, accretion is an efficient process. New ices accumulate on grain surfaces continuously. Over time, this accretion can rebuild mantles and modify grain composition. As atoms and molecules accrete onto grains, they form new mantles or change the composition of existing mantles. Material accreted in one environment might be different from the original mantle. Atoms from different regions of the galaxy created in different stars might accumulate on a grain. The grain thus becomes a record of the various environments through which it has traveled. A grain that has traveled through multiple stellar regions and molecular clouds accumulates a complex history in its layered structure. The net balance between destruction and growth sets the overall dust budget. The dust abundance in any region of the galaxy results from a balance between processes that destroy dust and processes that create or grow it. In regions with active star formation, where shocks and radiation fields are common, destruction dominates. Dust is consumed faster than it is created. Dust is depleted. In quieter regions, or near sources of fresh dust like late-stage evolved stars, creation or growth dominate. Dust abundance increases. The net effect of all these competing processes determines the dust amount. The lifetime of dust in any region depends on the balance between these opposing forces. In dense clouds, coagulation tends to build larger, more porous grains. In regions where dust grains move slowly and collide gently, coagulation dominates. Grains stick together, forming larger aggregates. Over time, these aggregates grow. The resulting grains are larger than would be produced by simple grain growth because they are made of multiple smaller grains stuck together. The structure is fluffy and porous because the individual component grains are not perfectly packed. These fluffy aggregates have different optical properties than compact grains. They scatter and absorb light more efficiently, gram for gram, than compact grains. In diffuse regions, ultraviolet processing can aromatize carbonaceous materials, making them more PAH-like. Carbonaceous dust in diffuse regions is exposed to ultraviolet light. Ultraviolet processing can transform the structure of carbonaceous molecules. Aliphatic structures can be converted to aromatic structures. The material becomes enriched in PAHS, the flat ring structures discussed earlier. This aromatization changes the optical properties of the dust, shifting its absorption and emission characteristics. Diffuse region dust thus has different properties than dust in dense clouds, partly because of the effect of ultraviolet processing. The universe naturally sorts dust by environment, creating populations with distinctive properties. Dust evolution influences the shape of the extinction curve over time. The extinction curve, that describes how extinction varies with wavelength, is not fixed. As the dust population evolves, the extinction curve changes. Different dust compositions and grain size distributions produce different extinction curves. By observing extinction curves in different galaxies and at different cosmic epochs, astronomers can track how dust populations have evolved. Young starburst galaxies show different extinction curves than old quiescent galaxies. The extinction curves of galaxies at different distances, and thus at different times in cosmic history, reveal how dust has changed over billions of years. Regions with more small grains tend to show steeper ultraviolet extinction. Smaller grains are more effective at scattering ultraviolet light than larger grains. In a region where the grain size distribution is weighted towards smaller grains, the ultraviolet extinction will be larger. The extinction curve will be steeper. This relationship provides a way to infer grain size distributions from extinction curves. When astronomers observe a steep extinction curve, they infer a population rich in small grains. When they observe a flatter curve, they infer a population with more large grains. The extinction curve thus contains encoded information about grain sizes. Environments with more large grains produce flatter extinction and less reddening. Conversely, in regions where large grains dominate, the extinction curve is flatter and reddening is less pronounced. Large grains scatter light less efficiently at optical wavelengths and particularly at ultraviolet wavelengths, resulting in less dramatic extinction curves. In such regions, visible light passes through relatively unimpeded, while infrared light absorption remains significant. The extinction curve becomes flatter, indicating a dust population dominated by large grains. Observations of different galaxies show systematic trends in dust properties with metallicity. Metallicity, the abundance of heavy elements, varies among galaxies. Galaxies with high metallicity, those that have been enriched by many generations of stars, have different dust properties than metal-poor galaxies. Dust abundance correlates with metallicity. The amount of dust grows as a galaxy becomes more metal-rich. This makes sense because metals are key components of silicate and iron-containing dust. More metals mean more opportunities for silicate and metallic dust formation. The extinction law varies with metallicity, with more metal-rich galaxies showing different extinction curves than metal-poor galaxies. Young, low-metallicity galaxies often have less dust and different extinction laws. Early universe galaxies and modern dwarf galaxies that have experienced few stellar generations are metal-poor. These galaxies have less dust than metal-rich galaxies. The dust that they do have has different properties, different extinction curves. The grain sizes and compositions differ because the dust population is young and has not been processed extensively. Early universe galaxies, observed when the universe was young, show evidence of less dust and different dust composition than modern galaxies. This reveals how the universe has been enriched with dust over billions of years of stellar evolution. Within a single galaxy, dust characteristics can vary between spiral arms, bars, and halos. Galaxies are not uniform. Within our Milky Way, dust is concentrated in the disk, less abundant in the halo. Within the disk, dust is concentrated in spiral arms, less abundant in interarm regions. Even within spiral arms, dust concentrates in giant molecular clouds. This variation in dust distribution and properties reflects the underlying distribution of gas and stars and the history of star formation. Spiral arms are sites of enhanced star formation, where massive stars are born and die, injecting radiation and shocks that modify dust. Halos are regions where older stars dominate, and star formation is minimal. The interplay of star formation, stellar feedback, and gas flows sculpts dust distributions. The distribution of dust in a galaxy is not random or static. Rather, it results from dynamic processes. Star formation creates dust in stellar winds and explosions. Stellar feedback, the effects of radiation and winds from massive stars and supernovae, can destroy dust or drive it outward. Gas flows throughout the galaxy, driven by gravity and other forces, move dust from place to place. The net result is a dust distribution that constantly changes yet maintains broad patterns. Computer models of galactic evolution attempt to simulate these complex processes, predicting how dust distributions evolve over billions of years. Dust is carried into galactic halos and outflows, seeding the circumgalactic medium. Not all dust remains in galaxies. Some dust is driven outward by stellar feedback, escaping the galaxy. This dust travels through the halo surrounding the galaxy, the circumgalactic medium, extending outward to the edges of the galaxy's influence. This dust-enriched outflow carries metals and dust from the galaxy into the intergalactic medium. The dust in these outflows can travel to distances of hundreds of thousands of light-years from the galaxy. The circumgalactic medium of a galaxy is thus enriched with dust driven out by stellar feedback. Some dust grains may eventually be expelled into intergalactic space. Dust from galactic outflows does not remain near its parent galaxy indefinitely. Some dust is eventually lost entirely, escaping into the vast empty spaces between galaxies. This dust, created in stars and processed in galaxies, enters the intergalactic medium. There, it will never return to form new stars, at least not until the distant future, when different physical processes might reunite the dispersed material of the cosmos. Some theoretical models suggest that in the very distant future, after trillions of years, the universe might cool and collapse, reuniting the dispersed material. But on human timescales, dust lost to intergalactic space is gone forever. Through all these processes, interstellar dust weaves a quiet, evolving web that links starlight, gas, chemistry, and the birth of new worlds. From the largest scales, galactic structures, and the evolution of galaxies, to the smallest scales, individual molecules on grain surfaces, dust plays a role. Dust connects the physics of stars to the chemistry of complex molecules to the biology of planets and life. Dust is old, ancient as the galaxy itself, yet constantly renewed by stellar births and deaths. Dust is ubiquitous, found in galaxies across the universe, yet varies from place to place in its properties and abundances. Dust is both the remnant of stellar deaths and the seed of stellar births, both the destroyer and the creator. In its microscopic grains, the universe inscribes the story of its own evolution and the creation of worlds. Closing meditation. As we come to the end of our journey through the mysteries of interstellar dust, take a moment to reflect on what you have learned. We have traveled through space and time, exploring the smallest particles and the grandest structures. We have seen how dust, invisible to human eyes, shapes the visible universe. We have discovered that the dust between the stars is not empty or meaningless, but rather central to everything that exists. The atoms that compose your body were forged in the cores of dying stars. Some of those atoms may have been incorporated into dust grains that traveled through the galaxy for billions of years before they were incorporated into the Earth. You are connected to the universe not by observation alone, but by fundamental composition. The very substance of your being is cosmic substance. Remember this as you drift towards sleep. The universe is vast, ancient, and profound. Your worries and cares are temporary against the time scale of galaxies and stars. Yet you are not separate from this vast cosmos. You are part of it, made of its substance, connected to all other matter by bonds of gravity and physics. Let your mind settle. Let your breathing slow. Imagine yourself drifting through space, surrounded by stars and dust. Imagine the dust particles floating gently through the darkness, silent messengers of creation. Know that somewhere in the galaxy, in clouds hidden from any telescope, new stars are being born from dust. Somewhere, planets are forming. Somewhere, the universe continues its eternal dance of creation and destruction. May you find peaceful rest, knowing that you are part of this eternal cycle, connected to the stars and the dust that fills the spaces between them. Sleep well and dream of the cosmic wonders that surround us all.